Welcome back everyone to section 2, exponential functions and models. Again, we're going to take another leap up in difficulty here. Last time we talked about quadratics, before that it was linear functions. Now we're moving on to exponential functions. Right? Exponentials kind of have a lot of rules and stuff that go along with them. So actually in this video, I'm going to hold off on the applications. We're going to go over that in class. But instead, I want to make sure that we have a good foundation, right? I want to build our base a little bit and make sure that we really understand some of these rules that go along with exponentials. So, I guess let's get to it, right? So this first definition I want us to recall, right? Back in the good old days when we were first learning about exponentials, we had something, right, this notation. This is really notation, b to the nth power. So long as n is an integer anyway, the way that you should be thinking about these things is that this is b being multiplied by itself, and you keep going until you have n of them all together. So this is n times. So this is really just b being multiplied by itself. And the n, the exponent, is telling you how many times that it multiplies by itself. Okay, so using that definition then, the claim is we actually get quite a lot. That we can come up with these laws of exponents on our own, more or less. So let's think about this logically, right? I'm going to choose some specific values for b's and x's and things like that. So maybe in this first case, I'm going to choose b to be 2, and x I'll do 3, and y I'll do 4. And so the claim is we can guess what this is trying to tell us just by looking at this special case right here. So maybe let's use our definition here and realize that 2 to the third power is just 2 times 2 times 2. And 2 to the fourth power is 2 times 2 times 2 times 2. Right? And so it looks like, right, because there's multiplication in between here, that there are a lot of 2's here. In this case, there are 7 2's being multiplied by itself, right? 7 2's altogether. So this is going to be 2 to the 7th power, right? And this is really using, I guess, technically the associative property for multiplication. So, I mean, basically it just says that it doesn't really matter with these parentheses, right? So if I wanted to get 7 from 3 and 4, right, I have to add those together. So notice the base stays the same. The 2 is the exact same. So I'm going to do b over here. But then it should add the exponent. So this should be x plus y. So again, this is very logical. This isn't anything that you need to memorize, right? This is something that we can come up with whenever we need, right? Again, it's logical. Let's try to see what this other one's trying to tell us here. So this part b here, let me go ahead and write it down. If I had 2 to the 4th power and I divided by 2 to the 3rd power, right? So a very specific case. Well, that'd be 4 2's in the numerator, 3 2's in the denominator, and it looks like some would cancel, right? So some 2's would cancel out here, and so I just have 2 left over, or 2 to the 1st power if you'd like. Right, so, okay, this is saying that somehow, right, in order to get 1 from 4 and 3, I'd probably subtract, right? So that this should be b to the x minus y. So that's 2 to the 4 minus 3. Right, so 4 minus 3, that's the 1st power. That's 2 to the 1st. And it's because there's cancellation, right? The cancellation is what's going on here. Okay, let me actually skip C for a second. I'm going to go on to D. And we probably have seen this before, and you can plug it into your calculator to verify, but really anything raised to the 0 power is going to be 1. I guess the only case that you really have to worry about is 0 to the 0 power. That's really weird. But luckily, b is greater than 0, so we really don't have to worry about negatives or when it's equal to 0. So yes, whenever b is positive and you raise it to the 0 power, that for sure is going to be 1. So there we go. That's 1 there. And now the claim is this is going to help us figure out what c is trying to tell us. Right, so if I have, maybe let's do 1 over 2 to the 4th power, or something like this, right? So I'm choosing a specific b and x. Well, we could rewrite this, right? Instead of 1, I could write 2 to the 0 power, and down here, still 2 to the 4th power, right? Because according to D, 1 is the same thing as 2 to the 0 power. So now, according to B, right, I would subtract these. So this would be 2 to the 0 minus 4. That's according to B there. And then I could simplify this down, so this is going to be 2 to the negative 4th power. So the answer here is that this is b, and it's not to the x, right? Because here is positive 4, here is negative 4. But you can switch it from a denominator to a numerator. Oops, it looks like I erased a little too much. You can switch it from a denominator to a numerator so long as you make it negative, right? So that's a pretty nifty rule here. It turns out we'll use this one a lot. Okay, e. E again is very logical, so let's go ahead and look at this. If I had 2 to the third power, and then I raised it to another power, let's do to the fourth power maybe. So this is going to be 2 cubed, right? And altogether there's going to be 4 of them. Well, each 2 cubed, right, I know what that is. That's just 2 times 2 times 2. So 2 times 2 times 2. And altogether there's 4 of these. Looks like I'm not going to have a room. I'll just break out of my box here. So how many 2's are there altogether? It looks like 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And they're all being multiplied to each other, right? So this is 2 to the 12th power. So how do I get 12, right? The base is the same, it's still 2. How do I get 12 from 3 and 4? Well, you would multiply them, right? So this is b to the x times y. Okay. How about f, right? Let's do, I have 2 different bases now. So I'm going to do 2 and 3, and they're going to be all raised to the 4th power. So this is going to be 2 times 3, 2 times 3, 2 times 3, right, 4 times. And multiplication doesn't really matter the order in which you do this. This is called the commutative property. So I'm going to group all the 2's together. And then I'm going to group all of the 3's together. And I can recognize that this is 2 to the 4th power, and this is 3 to the 4th power. So this is saying that you can essentially distribute this exponent here, this 4, to the 2 and the 3, and that works out. This is a legal move. So this is b to the x and c to the x multiplied together. All right, one more. I'm going to do 2/3, right? Some b and c all raised to the 4th power. So this is going to be 2/3 times 2/3 times 2/3. And again, a lot of this just comes down to that definition. Oops, that's not a very pretty 2. Let's erase that one. 2/3. And so, okay, multiplying all the 2's, right? I know how to multiply fractions. I would multiply all the numerators together, and I would multiply all the denominators together. So this becomes 2 to the 4th, 3 to the 4th, right? So this is just saying, right, I can again distribute this raising to the 4th power to both the numerator and the denominator. So this is going to be b to the x over c to the x. Okay, so again, pretty logical, all things considered. So these are nice expressions, but really what I want to use is, right, exponential functions. So I want to apply these to exponential functions. So let's go ahead and remind ourselves. The claim is this came up in chapter 1, section 2, but I want to have it in these notes as well. So exponential functions are functions that look a certain way, right? They can be written in the form, and I'll use f of x is equal to a b to the x. So it's a times b to the x. Okay, or, I mean, we've been doing as well, right? Y is equal to a times b to the x. So either way, right, this is a function, exponential function. And the claim is, right, we needed some conditions in order to make this a true exponential. So these were these conditions here. If you want it to be a true exponential, b should be greater than 0. It should not be equal to, not 0. That's already solved. B should not be equal to 1. There we go. And a should not be equal to 0. Otherwise, it's not really a true exponential. And then finally, right, I've been saying this a few times, but I want to have it in our notes, that we call b the base of the exponential function. Okay, so we have a calculator, right? And we're going to check our results in our calculator here. But the claim is, anytime you come across a function that you really don't know what it looks like, you should fall back on this point plotting method. So I'd like to review this with us, and then I'd like to go ahead and use our rules of exponentials that we have to go ahead and plot these functions. So I'm going to go ahead, draw here. I'm going to do green first. So I'm going to plot these two functions. I'm going to do f of x in green. So with a point plotting method, right, you make usually a table, x and f of x, or x and y values, and you choose things for x, right, to plug in, and you see, okay, what does the function spit out? So maybe I'm going to plug in 0. That's usually a classic, right? So 3 times 2 to the 0 power, great 0, there we go. And so we can use this property right D here that says, well, anything raised to the 0 power is just 1. So I'm going to go ahead and say 2 to the 0 power is just 1. 3 times 1 is going to be 3. So if you plug in 0, you should get out 3. 1, 2, 3. There it is. Okay, how about if I plugged in 1? If I plugged in 1, 3 times 2 to the first power, well, 2 to the first power is just itself, right? 2, so 3 times 2 is going to be 6. So if you plug in 1, you get out 6. 4, 5, 6. Something like that. Let's do one more in this direction. 3 times 2 squared, right? Plugging in a 2 everywhere I see an x. Right in here, just plug in that 2. So, okay, that's going to be 3 times 4, that's going to be 12. I probably don't have enough room, but you can kind of see it's going off, getting very, very positive in this direction. Let's go in the other direction. If I do negative 1. So 3 times 2 to the negative first power. This is where it's really useful. Like I said, I'm going to be using this property a lot, the C property, right? Actually, I'm going to be going in this other direction, right? I have something with a negative exponent, and I want to know how to interpret this, right? Well, first I could plug it into my calculator, right? But let's go ahead and use this really quick and show, okay, this should be 1 over b to the positive x power. So this is going to be, well, the 3 is just along for the ride, and this is going to be 1 over b, so it's 2 raised to the positive x power. So this is going to be 1 over 2 to the positive 1. Well, 2 to the positive 1, that's just 2. So this is going to be 3 halves. Okay, so if I plug in negative 1, I should get out 3 halves, so that's going to be like 1.5-ish. Let's do one more point here. If I did negative 2. 3 times 2 to the negative 2 power. Again, I'm going to use that same rule here. 1 over 2 to the positive exponent here. So this is going to be 3/4. So a little bit less than 1. Okay, so like I said, we can do this in our calculator. Let's go ahead and check really quick. So I'm going to pull out my calculator here. And I want to just check, right, 2 raised to the negative 2. So 2 raised to, then you have to use parentheses here. Parentheses, negative 2. Close parentheses. Hit enter. 0.25, so that's the same thing as 1/4, right? And let's go ahead and multiply that by 3. And so you can see our final answer, right, should be indeed 3/4, or 0.75. So yes, this does work out, but it's nice to be able to do these things by hand sometimes. Okay, so we know that this is going to look something like this. And exponentials, right, they have kind of this, we've seen this back from 1.2, that they seem to have an asymptote. They get closer and closer to 0, but they never really cross. Okay, let's try the other function here, g of x. And actually, before I even get started here, let's use my last property that says, hey, you can distribute exponents. Let's go for it. So this is going to be the same thing as 1 to the x over 3 to the x. And this is really nice because 1 raised to any power is just 1. So we were able to simplify this function down a little bit before even getting started. So let's go ahead and again use the point plotting method, x and g of x here. And so maybe if I started by plugging in 0, right? So if I plug in a 0 everywhere I see an x, that's going to be 1 over 3 to the 0. I know anything raised to the 0 power is just 1. So that's just going to be 1 over 1. That's going to be 1. So when I plug in 0, I get out 1. So that's my y value, 1. Okay, how about if I plugged in 1? This is relatively straightforward. That's just 1/3. Okay, so that's going to be somewhere down here maybe. And one more, maybe 2. 1 over 3 squared. That's going to be 1/9. And that's getting, again, closer and closer to 0 here. How about if I go in this other direction here, negative 1. So if I plugged in negative 1 for x, then I'd have 1 over 3 to the negative 1 power. Ugh. So I can use my calculator, but the claim is we can also use this property c here, right? So I have 1 over 3 to the negative first power here. So my x is negative 1. So I can trade this in for 3 raised to the negative x. Again, my x is negative 1, so negative 1. Negative 1 is just going to be 1. right? So the claim is this is just 3. That's pretty nifty. But, again, I'm a little bit paranoid. Let's go ahead and check this in our calculator really quick. 1 over, I'm going to do parentheses, 3 raised to the, another set of parentheses, negative 1. Close, close. Enter. That is indeed 3. Nice. Okay, so when I plug in negative 1, I get out 3. So I plot that point. One more if I did negative 2, right? 1 over 3 to the negative 2, right? Well, again, this is going to be 3 raised to the negative 2. That's going to be 3 squared, or that's the same thing as 9. I might have room for this one. 6, 7, 8, 9. So right up here. So here's what this looks like. Again, right, let's check these results in our calculator really quick. So here's my calculator. This actually gives us a really fast way. Oops, let me clear these out really quick. So let me go ahead and graph the first one. 3 times 2 raised to the x power graph. And I think from before, I had this zoomed differently. So let me go ahead and zoom. I'm going to go down to zoom fit just to see what the picture gives me here. So if I zoom fit for this one, what kind of picture does it give me? Oh, so it's flat for a while, and then it starts to go up, and then whoosh. All right, so this is zoomed way out here. But the nice thing about graphing it in our calculator is that there's this option for table here. So if I do second graph, I get a table. So you can see, first of all, this should match our table pretty closely. If I go back a few. So if negative 2 gives out 0.75, perfect. Negative 1 gives out 1.5, perfect. 0 gives out 3, perfect. 1 gives out 6, 2 gives out 12, and so you can get you can get a lot of values very quickly, right? So this is very nice to use our calculator to get the table. Let's go ahead and plot the other one then. So let's see, I'm going to go ahead, I guess just clear. Okay, so 1/3 over, oops, I missed the 1. 1 over 3, close parentheses, raised to the x power graph. Now I'm probably going to have to reformat this again. Oh, it actually doesn't look half bad. So you can see kind of it zooms down and then it just kind of stays there for a while. Let's look at the table. So second table. And hopefully this matches. When you plug in negative 2, you get out 9. Yes. If you would plug in negative 1, you get out 3. Perfect. When you plug in 0, you get 1. Excellent. When you plug in 1, you get 0.33333. Of course, that's the same thing as 1/3. And if you plugged in 2, you get 0.11111. That's the same thing as 1/9, I hope. Let's go ahead and double check. Right? 1 divided by 9, is that the same thing? Yes. 0.11111. Excellent. Okay, so yes, our calculators are very powerful. So in fact, we actually showed, last time, exponentials always seem to have a certain look about them, right? Depending on if A is positive or negative, and depending on where B is, right? So let's go ahead. I'm going to make a quick table here to just kind of model this for us. Here we go. So if A is positive, if A is negative, and then if B is greater than 1, and if B is less than 1. Remember, we don't, oops, that's a horrible one. B is less than 1. Remember, B is we always take to be positive, so we take it to be something like this. And so the claim is, again, these have a certain look about them. So in this first case, f of x, you can see our A was positive, 3, and our B value, our base, was 2, right? So this was greater than 1. And in this case, it kind of zoomed off. It was an increasing, something like this, right? So that's what the look was. In the second case here, we had our A value was technically a 1, and our B value, well, this was actually less than 1, right? It's 1/3, that's our base. So we're in this case down here, right? So, okay, in that case, the exponentials looked something like this. So it was decreasing, but it was still positive. And then the claim is over here, Well, they kind of look the same except for it's flipped over this x-axis, so it looks something like this. Kind of zooms off negatively. Same thing, it looks kind of like this case over here, but it's flipped. So it looks something like this. So the claim is, right, these things have a certain look and feel about them. Again, let me bring up our Desmos. Oops. There we go. This is it. A times b to the x. And you can see if a is positive, oops, let's do a b value positive starting off. So maybe b is 1.6. So if a is positive and b is positive, oops, they all look like this, right? Something like that. And then if a is negative, right? Now they're all decreasing. So that's the other picture that I had drawn down here. Right, so when a becomes negative, they go like this. Okay, and then the other case, if b is less than 1, let's start off with a positive a first, right? That's kind of like our 1/3 raised to the x. They all look like this. Again, no matter kind of whatever the a value is, as long as it's positive. And then if a becomes negative, shoop, right? And now it's been flipped. Flip, 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 flipping over the x-axis. The claim is, so again, they all kind of have this sort of look about them. Okay, well, that's the end for this video. I'll see you next time. We'll talk about logarithms. See you then.